Welcome back. This is an Aleks training video on calculating the reaction rate of one reactant from that of another. Whenever you are making something, the stuff you use to make it with is disappearing. And the balanced equation that you have seen so much this year is used to tell you how much is going away at the same time of how much is being produced. So they're asking you to do a reaction between methane gas and steam, which is water gas, to make carbon monoxide and hydrogen. So I wrote it out. They would ask you to do that. I wrote it out and then I balanced it, and I wrote it at the top to help you. So I have methane gas plus water vapor yields carbon monoxide gas plus hydrogen gas, and it's a 1 to 1 to 1 to 3 relationship. So the balanced equation, we can see anything at the left is going to be used up. Anything at the right is going to be produced. So not only is 1 mole of methane used up for every 3 moles of hydrogen made, but you could use that for the time. The time it takes 1 mole to be used up is the same amount of time it takes to make 3 moles of hydrogen. So you can use this to help you to know what the rates are. So in the problem, let's read the problem. Suppose a chemical engineer studying a new catalyst for a reform reaction finds that 540 liters per second of methane are consumed. All right, so that's a reaction rate for methane. You have 540 liters being used up, and in that same amount of time per second, you're going to see that so much hydrogen is going to be made. Now, I can't guess from liters. I can't say 540 liters of methane is going to be used up for 3 times that amount of hydrogen. The only thing the balanced equation tells me is number of moles. So if I knew the rate of going away for the methane in moles per second, then I would know that it's 3 times that for the hydrogen. The only way that I would know to do a liters to moles is to use the ideal gas law. So we have PV equals nRT. So if I solve for N, it's going to be RT. So PV equals RT is N. And then I can fill in what they've told me. I have 540 liters. I have 0.90 atmospheres. The R value whenever you have atmospheres is going to be 0.820574. That's your R. And then your temperature has to be in Kelvin. So I have 297 plus 273.15 gives you 570.15. This gives you a total N of 10.38793895. Okay, moles per second. Now I can use the balanced equation, or the balanced equation, to find out what the rate of the hydrogen is. Okay, so coming up here, 1 is to 3 as 10.38 is 2. That's what we're going to be doing. Okay, so we see that 1 mole of methane is to 3 moles of hydrogen as 10.3879 moles of methane is to what? Okay, so I find that that is 31.16381684 moles per second. Now they ask for kilograms per second. So to go from moles to kilograms, to go from moles to grams, I have to go through the molar mass on the periodic table. So I have 31 point, well, let's just do a few units. I'm going to have to round probably to two units at the end anyway. So this is moles per second. Now, hydrogen gas is H2. Okay, so H2 is going to be 2.01588 grams per mole. Moles will cancel, and now I'm in grams per second. So 2.01 times 31, okay, gives me 62.83 grams per mole. And then I want kilograms, so I have to divide by 1,000. So this is going to equal okay. Now I've gotten it to 2 significant digits. I think I need 2. Okay. Yep. Because 90 atmospheres is 2 significant digits. Okay, so I need this. And that is the rate of hydrogen production. Okay. So pretty hard, not too hard. I think you can get it. We'll work on it.